Our sun is a massive ball of burning gas, a colossal sphere of plasma that fuels life on Earth. It's not just light and heat that it provides, it's a giant active nuclear reactor, constantly undergoing fusion reactions. Sometimes the sun releases sudden bursts of energy. These explosive events are known as solar flares. Imagine a sudden, intense flash of light and energy, brighter than anything you can see on Earth. That's a solar flare, and they can have significant impacts on us here on Earth. These flares are incredibly powerful. They release energy equivalent to millions of atomic bombs exploding simultaneously, unleashing a tremendous amount of power. This energy travels through space at incredible speeds, sometimes reaching Earth in just a few minutes, covering the vast distance in no time. When these solar storms hit Earth, they interact with our planet's magnetic field and atmosphere, causing a variety of effects. One of the most beautiful effects is the auroras, also known as the northern and southern lights, which light up the night sky with vivid colors. However, solar flares can also disrupt satellite communications and GPS systems, causing significant challenges for technology. In extreme cases, they can even cause power grid failures, leading to widespread blackouts and requiring engineers to work tirelessly to restore power. Scientists continuously monitor solar activity using advanced equipment to predict and mitigate the impacts of these solar explosions. Spacecraft and astronauts are also at risk, and protective measures are essential to safeguard them from the harmful effects of solar flares. The sun, in all its glory, is a reminder of both the power and beauty of our universe, a celestial body that sustains life and challenges us with its explosive nature. As we watch the sun set over the horizon, we are reminded of its constant presence and the dynamic forces at play within it. The night sky, filled with stars, serves as a testament to the wonders of the universe and the incredible phenomena that occur within it. We use radio waves for communication. These invisible waves are the backbone of modern technology, enabling us to send and receive information over vast distances. Radios, TVs, and even GPS systems rely on these waves. They are essential for broadcasting music, news, and navigation signals that guide us in our daily lives. However, solar flares can disrupt radio waves. These powerful bursts of radiation from the sun can interfere with the signals we depend on. Imagine static on a radio during a thunderstorm. The crackling noise and loss of signal can be frustrating. A solar flare can cause similar interference, but on a much larger scale. The impact is not just limited to a small area, it can affect entire regions or even the whole planet. The energy from a solar flare can ionize the Earth's atmosphere. This process involves adding or removing electrons from atoms and molecules, creating charged particles known as ions. This means it can strip electrons from atoms, creating ions. These ions can then interact with radio waves, causing them to scatter or be absorbed. These ions interfere with radio waves, making communication difficult or impossible. The more ions present, the greater the disruption to the signals. This interference can impact everything from emergency broadcasts to air traffic control. In critical situations, reliable communication is essential for safety and coordination. Scientists continuously monitor solar activity to predict and mitigate these disruptions. By understanding the sun's behavior, we can better prepare for and respond to solar flares. Technological advancements also help in designing more resilient communication systems. Innovations in this field aim to reduce the impact of solar interference, ensuring that our vital communication networks remain operational. As we look to the future, the challenge of solar interference will continue to drive research and development. Our ability to communicate seamlessly, even in the face of solar flares, will be a testament to human ingenuity and resilience. Scientists study the sun to understand and predict solar flares. These powerful bursts of radiation can have significant effects on our planet, making it crucial to anticipate their occurrence. They look for sunspots, which are cooler, darker areas on the sun's surface. These sunspots are indicators of the sun's magnetic activity and can provide valuable clues about upcoming solar flares. Sunspots are like magnets, with north and south poles. The magnetic fields in these regions are incredibly strong and complex, often interacting in unpredictable ways. When these magnetic fields connect and realign, they can release immense energy, a solar flare. This process is known as magnetic reconnection and is a key driver of solar flare events. The more sunspots, the more active the sun. Increased sunspot activity often correlates with a higher frequency of solar flares, making it a critical factor for scientists to monitor. This means a higher chance of solar flares and potential disruptions to our communications. Solar flares can cause radio blackouts, affect satellite operations, and even impact power grids on Earth. By tracking sunspots, scientists can anticipate solar activity and issue warnings. These warnings are essential for preparing and protecting our technological infrastructure from the adverse effects of solar flares. Solar flares are classified by their strength. Smaller flares might cause minor radio blackouts in specific regions. Larger flares can disrupt communications across entire continents, lasting for hours. In extreme cases, they can even damage satellites and power grids. Understanding the different types of solar flares helps us prepare for their potential impact. By knowing what to expect, we can take steps to mitigate the risks and ensure the resilience of our technological infrastructure. Section 5. Predicting the sun's temper. Predicting solar flares is crucial. It gives us time to prepare and minimize disruptions. Scientists use sophisticated telescopes and computer models to monitor the sun's activity. They track sunspots, solar flares, and coronal mass ejections. Just like weather forecasts on Earth, space weather forecasting is becoming increasingly accurate. The more we understand the sun's behavior, the better we can predict these events and protect our technology-dependent world. Section 6. The Carrington Event, when the telegraph went wild. In 1859, the largest solar storm ever recorded hit Earth, the Carrington Event. Telegraph systems worldwide went haywire. Operators received electric shocks and some telegraph lines sparked, setting fires. Imagine the chaos if such an event happened today. Our reliance on technology is far greater than in 1859. A Carrington-level event could cripple communication networks, power grids, and satellite systems, causing widespread disruption. Section 7. Modern impacts and the need for resilience. Solar flares have caused significant disruptions in recent times. In 1989, a solar storm knocked out power for millions in Quebec, Canada. In 2003, another storm disrupted GPS signals and caused radio blackouts. These events highlight the vulnerability of our technology. As we become more reliant on technology, we must also invest in making our systems more resilient to space weather events. Section 8. The future of space weather forecasting. Space weather forecasting is an evolving field. Scientists are constantly working to improve their models and predictions. New telescopes and spacecraft are providing unprecedented views of the sun, helping us understand its behavior in greater detail. The future of space weather forecasting is promising. With continued research and advancements in technology, we can better protect ourselves from the sun's powerful outbursts and ensure a safer, more connected future.